Hi, in the last two videos, we went first through Tabular Series and were allowing us to transform a polynomial function into an equivalent expression, and we learned that we could expand this function from a point 0 and write it in a different form. However, we noticed that this is very inconvenient because 0 is one specific value among infinity we could choose from. So then we introduced Tabular Series, that is a generalization of Tabular Series, and it allowed us to expand a polynomial function at any point. However, as we said before, it is still not very efficient tool, right? All we did, this far, is we were taking polynomial function and we were writing it in a different way. However, as I told you, that was more of a preparation of what's to come. And what's to come is Taylor's theorem. Taylor's theorem extends what we learned one step further and makes it, in this very instance, a very powerful tool. So now we are going to apply Tabular Series not only to polynomial function, but now there can be any arbitrary function. Okay, so let's go first through the theorem. Given an arbitrary function phi of x, so this can be any function, as long as we can calculate its derivatives, of course. If we know the value of the function at some specific point, x equal to x0, and the value of its derivatives evaluated at x0, then phi can be expanded around x0 as follows. And look, what do we see over here? Here is a tabular expansion, exactly the way we see it. Phi of x0 divided by 0 factorial. Phi prime of x0 divided by 1 factorial x minus x0. Phi b's of x0 divided by 2 factorial multiplied by x minus x0 squared. And we go like this until we arrive at phi, at nth derivative of phi evaluated at x0, of course, divided by n factorial times x minus x 0 to the power of n. However, you might notice that something new appeared over here. Because before we were basically rewriting polynomial function from one form into the other, that was enough, right? That was enough to transform given polynomial function into the same polynomial function, basically just written in with different expressions. However, look, if the function we are trying to approximate is not a polynomial function, then if we're going to try to approximate it using polynomial function, there will be a difference, or a reminder, as you might say. Look, this situation can appear even in the context of polynomial functions. Why? Because let's look what we've obtained over here. Look, expression that we're going to get from this is a polynomial, right? Nth degree polynomial. So this will be nth degree polynomial function. And look, what if original function is of degree n plus 1? Well, we will still not get a perfect fit. We will have remainder. And, of course, what you see over here is called remainder. And this remainder actually is showing us by how much are we mistaken if we are approximating any arbitrary function using a Tabular expansion. And look, we will get approximation of this function with the polynomial, and remainder will be our error of approximation. In other words, when we apply the theorem, we are trying to simplify more complicated functions with simpler polynomial. However, we're not always gonna get perfect fit. This is why we need to have a remainder. And look, this expansion can be done in various different ways. What I mean is that, for example, I can use linear approximation. Look, what does it mean? This means that if phi of x, let's just say some very complex functioning structure, I think that it's too complex, it's hard to deal with, and maybe it's not necessary. Why not make it into a simpler function, right? How would we do it? If we are talking about linear approximation, it means that n, the degree of the polynomial, is 1, right? So we are simply assuming that function that gives us linear approximation is just two components. So phi of x0 over 0 factorial plus phi prime x0 over 1 factorial times x minus x0, right? But this means we're going to have in mind that this is our polynomial of degree 1 plus polynomial or remainder from the polynomial of degree 1. Okay, but look, we can go further. Maybe linear approximation is not good enough, because remember, the more terms we have in approximation, the harder it is to work with. However, the better the approximation. The more terms, the better approximation we are getting. So the next one we could try is quadratic approximation. Okay, and what do we get here? Now, we start similarly, right? We will have phi of x0 over 0 factorial plus phi prime of x0 over 1 factorial x minus x0 and plus phi b's of x0 over 2 factorial times x minus x0 squared. And of course this plus R2. So we've got polynomial of degree 2 as an approximation and the remainder. Could we go further? Of course, we could have cubic approximation. How would it work? We would have this element, and this element, right? However, we need to have element number 3. So we would have third derivative divided by, evaluated at x0, divided by 3 factorial, and x times x minus x0 to the power of 3. And look, with each more complex function, we are getting better and better approximation, right? However, sometimes, as it turns out, linear approximation is enough. For example, when we are evaluating equilibria in terms of their dynamic properties, when we build general equilibrium models, we use linear approximations because we just want to know what happens around some point, and this is good enough. Okay, so now let me just illustrate this with an example that should also illuminate where lies the value of the Taylor expansion. Okay, look, let's just say that we've got some quadratic function, and we want to expand it around some point. Okay, so let's just say that our function is equal to 5 plus 2x plus x squared. Now, the point of expansion, let's just say, is 1, and we're going to use linear approximation, right? So, we got that x is equal to phi of 1 over 0 factorial plus phi prime of 1 over 1 factorial times x minus 1, right? Plus prime, right? This is it. This is linear approximation. Okay, so let's just substitute to what we've got. This is 5 times this is 5 times 2 plus 2 plus 1 divided by 1, right? Then we need to calculate first derivative, and we see that this is 2 plus 2x, right? If I evaluate this derivative at 1, I'm getting this is 2 plus 2, so this is 4 over 1 times x minus 1 plus over. Okay, so here we've got 7 plus 4x plus 4x minus 4, right? Here is plus 1, I'm sorry, this is 8 minus 4, so this gives us 4x plus 4, of course, plus reminder, plus reminder. Okay, so we've actually calculated, we see that linear approximation of this quadratic function is equal to 4x plus 4, and of course a reminder. So this is our P1. Now, let's try to see how this approximation works. Look, you can clearly guess that if we are going to approximate the value of a quadratic function using a linear function, there is a lot of different traps that are waiting for us, right? Because we clearly see that we know that quadratic function has a parabolic shape, but linear function is just a straight line. Okay, let's draw the line that we've got over here. If okay, it should look more like this. This is 4. This will be negative. It has a top of -1 and 5, of course, and 4. Yeah, and it goes like this. Here we've got 5. Here we've got the other part of the parabola, right? So this is our phi of x, right? So x and w. Now, for approximation purposes, we use function for x plus 4, right? So this function is positively sloping, and it cuts y-axis through 4. But let's just notice one very specific thing. We were expanding at point 1, right? Let's see what is value of phi of 1. So this is 5 plus 2 plus 1. This is 8, right? And now let's do the same thing for our polynomial approximation, our linear approximation. This is 4 plus 4 is equal to 8. So look, we see here that when we are at the point of expansion, in our case it's 1, the value of the line of our polynomial, so our linear approximation, it should go through 4, of course. Sorry, let's bring it. Okay, now it works. So, now we see that the value of our linear approximation, right, 8, is exactly the same as the value of the original function. However, this is not true for any other point. And look, what I can tell you that is always going to be true is that at the point of expansion, Tabular approximation, doesn't matter of what degree, is always has the same value as the original function. But it happens only at this point. Only at the point of expansion. And you know, the interesting thing that happens is what is happening when we move away from this point. So, what happens when we move away from 1 is that, as you see, the difference between original function and the approximation is getting bigger and bigger and bigger and bigger and bigger. So, this should provide you a key insight into when do we need to use Tabular approximation. Look, if something interesting is happening over here, and at this particular point, and let's just say somewhere around this point, this is a very good idea to use Tabular approximation, right? If something that is interesting to us would here, right? Or some further over here, not a very good idea, right? So, for example, if you find some equilibrium in some model, you know more or less, you know where it is, but you do not know what is the value of this equilibrium, and it's too hard to calculate. Maybe it's a good idea to use linear approximation, see what happens at this particular point, and that's it, right? Not a big problem. Of course, sometimes it's better to use higher degrees polynomials. However, in most of the cases, we're going to be dealing with linear approximation is enough because it tells us what happens over here. And we remember that the further and further away we move from that point, the worse our approximation gets. Because look, here, this distance between these two functions is our error. This would be an error that we've got, and we see clearly whenever we move in any direction, it gets big. Okay, so look, now you know how to use Tabular expansion. Of course, in most of the cases, we're going to be using, it's going to get linear approximation is enough. Now, reminder, we haven't talked about this reminder much, because sometimes this reminder is interesting and sometimes it is not. Like in this case, the reminder doesn't have any meaningful interpretation, right? And in this also particular context, we are using very low degree approximations, right? Linear. So reminder is bound to be big the further we go from the function. However, there is one specific case where understanding the properties of reminder is extremely